This is my Calculus 1 course. Today we're going to learn some properties of definite integrals, and we're also going to learn the substitution rule. If you haven't done the homework completely incorrectly from the last class, do that homework before watching this video. First, we're going to learn some vocabulary. To integrate means to find antiderivatives of a function in order to calculate an integral. So we've been doing that, we just haven't been calling it integration, or we haven't used that verb. So for now on in this course, we're going to be using that verb quite a bit. And the left and right bounds of integration are called the limits. So if we have this definite integral, for example, a and b would be the limits of integration. So for example, 1 and 3 are the limits of integration if we try to find the value of this integral. Now, so far in this course, we have found the area between the graph of a function and the x-axis when the graph is above the x-axis. So the area has always been above the x-axis. But what happens when we have a situation where the graph is actually below the x-axis? If we find the value of an integral where the corresponding function is actually below the x-axis, what's going to happen? Well, let's see what happens. So the difference between these two graphs is that one graph is reflected across the x-axis, and in order to do that, you simply multiply all these terms by -1. So we have the same function just reflected across the x-axis. So we found the area under the curve, and it was 4 8/9 when the area was above the x-axis. But now let's figure out what it is when the area is below the x-axis. So we're going to find the antiderivative, which is 1/9 times x to the third minus x. And remember, we don't really need to write the c value when we find an antiderivative because c always cancels out. So remember, what we do is we write a bracket and then we write our limits of integration, and that tells us to plug in 3 into that antiderivative function and then subtract the same function with 1 plugged in. And so if we do the math, we get -1/9 times 27 minus 3 minus -1/9 times 1 minus 1, and so on and so forth. And we end up with -4 8/9. So when we found this area above the x-axis, it was +4 8/9. But when we found the same area, but it was positioned below the x-axis, we found the same number, except it was negative. Now, it's very important to understand that area in the real world cannot be negative. There is no such thing as negative area. But just by the definition of the integral, the definite integral, we can have values that are actually negative. So the integral itself, when you calculate, it can be a negative value, but that doesn't mean that there is such a thing as negative area. It just means that the integral is negative. So when area is above the x-axis, we have positive area. When it's below, we have negative area. Now, again, whenever we say negative area, we don't actually mean negative area. We just mean that the integral is negative. So let's do some practice problems where we have negative area. It says find the values of the integrals using the graphs only. So we're not going to use the fundamental theorem of calculus. And you can see that if we graph this function, we have a semicircle. So we want to find the area, and it's below the x-axis, so it's going to be negative. So I'm going to go ahead and put my negative symbol there. And to do this, we can find the area of the circle using that green formula up there, but we have to divide by 2 because it's a semicircle. So we have negative 9 pi over 2. So that's the area. Okay, so here's another example. We're going to find this area, but notice that the area is below the x-axis. So it's going to be negative area. And of course, we're just going to find the area of a triangle here. That's this formula up here, 1/2 base times height. Now you should know these formulas by now at this point in the math curriculum, but I'm just reminding you of those. So what is the base? Looks like the base is 4 and the height is 2. So base times height divided by 2, and we end up with negative 4. So again, why is the area negative? Because it's below the x-axis. But again, there is no such thing as negative area. We're just calling it negative because the integral is negative. So let's try another one. Well, here, of course, we just have a rectangle. And you might wonder, what does this integral actually mean when there's just a negative dx there? Well, that means negative 1 dx. So you're just finding the antiderivative of negative 1. But we're not finding the antiderivative. The graph is y equals negative 1. You see this over here. If you plot y equals negative 1, then it's just a horizontal line. And so the area is the area of that rectangle. The length is 1. And the width is 3. And of course it's negative area because the area is below the x-axis. So I want you to take a picture of this information, and I want you to try number 4. So again, do not use the fundamental theorem of calculus. You could use it, but that's not the point of these problems. You can just use these formulas up here because we have just basic geometric shapes. Again, remember, when you see an integral, it's asking you to find the if you see a definite integral, specifically, it's asking you to find the area under this curve here, which is that yellow area down there. And remember, it's going to be negative because the area is below the x-axis. So try number 4. When you come back, we'll do it together. Okay, we're back. So we have negative 2. If you got that right, excellent. So go ahead and try number 5. Again, don't use the fundamental theorem of calculus. Use your area formulas. So try number 5. When you come back, we'll do it together. Okay, we're back. So then we end up with negative 2 pi. So the area is negative 2 pi. But again, technically the area is not negative. It's just the value of the integral is negative based on the definition of the integral. Okay, so try number 6. Now for number 6, I want to warn you that you're going to have to use 2 formulas because you've got this triangle here. You see that triangle? That green triangle. But then you've also got this this rectangle there. You see the light green rectangle and the dark green triangle. So you're going to use 2 formulas. So try number 6. You can take a picture of these formulas if you want, and when you come back, we'll do it together. All right, we're back. So if you got that right, excellent. Okay, so that's what you get when you're trying to find area that's under the x-axis. It's negative. The integral is going to be a negative value. Now we need to learn some more vocabulary. We talked about these numbers in a definite integral being called the limits of integration. The left and right bounds, a and b, are the limits of integration. But specifically, a is called the lower limit of integration and b is called the upper limit. So we need to differentiate between those two numbers. So again, we're going to use these terms for now on, upper and lower limits of an integral. So the lower limit here, for example, would be 1, and the upper limit would be 3. That's kind of confusing to use the term limit because we use that term for obviously other things in this course, but that's just what mathematicians have decided. So we have to use that terminology. Now, in the previous problems, we found the area with the lower limit equal to 1 in our integral, and the upper limit was 3. So we found the value of this integral. Alright, but what if you switch the limits? What if you switch the limits of integration, reverse them? What if you change so that the lower limit is a bigger number and the upper limit is a smaller number? What do you get then? Well, that's what we're going to calculate now. So in the previous problems, we integrated moving from left to right, so to speak. You can think of sweeping left or right as we try to find the area. But now we're going to integrate moving in the other direction, from right to left. So what happens then? Well, let's find out. So we're going to use the fundamental theorem of calculus. So that gives us 1/9 x to the third power plus x. And we're going to go from 3 to 1. So the only difference is we switch these numbers. Usually we go 1 to 3. So now we're going to calculate. We're going to plug in 1 first. We're going to subtract that expression with 3 plugged in. And we get 1/9 times 1 plus 1 minus 1/9 times 27 plus 3. And long story short, we get -4 and 8/9. So our area was actually above the x-axis, but because we integrated going in the opposite direction, we got a negative number. So in the previous problems, we said that area above the x-axis is positive, but area below the x-axis is negative. But now we see that that's not exactly true. It depends on which way you're integrating. If you integrate in the opposite direction, you get an opposite sign. So just to be clear, up here, we found that area and it was positive 4 and 8/9, right? Because we are integrating from 1 to 3. But now we get -4 and 8/9, finding the same area because we integrated from 3 to 1. Not 1 to 3, but 3 to 1. So if you're wondering what happens if you reverse those limits of integration, those left and right bounds, that's what happens. It just changes the sign. So now we have an example where we're trying to find the area, the same exact area, but it's area below the x-axis. We've reflected the graph across the x-axis. But in the previous problems, we tried to integrate from 1 to 3. Now let's integrate from 3 to 1. And again, we found the area to be -4 and 8/9. But now if we integrate in the opposite direction, you can probably tell what's going to happen. But let's just do it real quick so you can see. So instead of integrating from 1 to 3, we're integrating from 3 to 1, and we're going to plug in 1. to the antiderivative, and then we're going to plug in 3 to the antiderivative and subtract. Whoops, I don't know why I wrote an x there. And we'll see what happens. So now we get negative 1/9 times 1 minus 1 minus negative 1/9 times 27 minus 3, and negative 1/9 minus 1 minus negative 3 minus 3, and we're out of room, so we can just calculate. And we get positive 4 8/9. So our area was below the x-axis, but we got a positive number. Why is that? Well, because we're integrating in the opposite direction. So it's kind of confusing. If you're integrating from left to right, the area above the x-axis is positive, below the x-axis is negative, if you're integrating from left to right. But if you integrate from right to left, then your area above the x-axis is negative and your area below the x-axis is positive. So, kind of strange. So this brings us to this property here. If you reverse the limits of integration, see how we reverse the a and the b? If you reverse, you change the sign of the integral. So this integral here is equal to this blue integral. They are exactly the same, no difference whatsoever, except they're different signs. So in order to make this equation true, you have to add this this negative symbol here. And so that changes the sign of the blue integral, making it equal to the yellow integral. So this is just a way to explain that if you flip or reverse the limits of integration, then you just change the sign of the integral. So if that's true, then if we find if we integrate sine x from negative pi to pi, we should get 0. Because if you remember your sine curve, these areas here should be equal areas. So if we start from negative pi and find the area of the sine, or the area between the graph of the sine function and the x-axis, that should be negative area. But up here we should have positive area. So if you integrate from negative pi to pi, we should actually get 0. They should cancel each other out, the areas. And that's if you're integrating from left to right. So let's see if it works. So let's find the antiderivative of sine. That's a negative cosine x. And we're integrating from negative pi to pi. And so we're going to plug in pi and then subtract the antiderivative with negative pi plugged in. And the double negative goes away. And there's a lot of different ways we can evaluate this, but you want to look at your cosine curve. Pi is right here. That's at -1. So we're going to have a double negative there. And cosine of negative pi, well, that's going to be if you go in the opposite direction, you still have -1 down here. So again, that's something you need to just memorize. That basic trig is just something that students need to memorize. So we have +1 minus 1 is 0. So that's exactly what we would expect. We got 0 area. It's not really 0 area, but the value of the integral is 0. Now, if you integrate in the other direction, then the area above the x-axis turns to negative, and the area below turns to positive. But again, if you integrate, you should if you integrate from negative pi to pi, you should get 0 area. So let's try. We have negative cosine x from pi to negative pi. So we're reversing the limits of integration, and we're going to plug in negative pi first this time, then subtract the antiderivative with positive pi plugged in. And cosine negative pi is -1, and cosine pi is also -1. You can do this however you want to, but we end up with 1 minus 1, which is 0. So an integral helps you to find area, but it's up to you to interpret that integral properly when it comes to area, because the integral will just spit out a number for you, but it may not be the exact, it may not be the area, because again, you can't have negative area, you can't have 0 area. If you wanted to actually find the area of these regions, you'd have to find the area from negative pi to 0, and then change it to a positive, because again, you can't have negative area. And then you have to find the area from 0 to pi, and then add those together, and that would be the actual area. Now, these problems here that we've been doing, it kind of demonstrates something we can call the integral decomposition property. And what that means is you can take an integral and break it up into 2 different integrals. Notice that if we find the integral, or if we integrate from negative pi to 0, we find this area here. Actually, this area, which is negative. And if we integrate from 0 to pi, we find this area here. But if we integrate from negative pi to pi, that's the sum of those 2 integrals. So it kind of demonstrates this property that you can actually break an integral into 2 integrals. So the integral, or the integral from a to b is equal to the integral from a to c plus the integral from c to b. So we're introducing a third number, c, which is normally between a and b, but it doesn't even have to be between a and b, as you'll find if you actually think about that logic. So in order to practice these concepts, we're going to do some more problems. It says find the value of each expression. So this is asking for the area between the x-axis and the graph of f of x between -3 and -1. So -3 and -1, that would be this area here, this yellow area here. And we're going from left to right, -3 to -1. So that means because this area is above the x-axis, the value of the integral is going to be positive. So that's just the length of that rectangle times the width. So the value is 6. Again, you can use these formulas up here, but you really should have those formulas memorized by now. Okay, so now we're going to find the area from 0 to 3, area between the graph of f and the x-axis from 0 to 3. But that's actually this area here, which is below the x-axis. And because we're moving from left to right, we know that that area is going to be negative. So the area of that triangle is 1/2 times the base, which is 3, times the height, which is also 3. And looks like we get 4.5. But it's going to be negative area. So let me add my negative. So there you go. Okay, so now we're going to find the area between the x-axis and the graph of f from -4 to 0. So we're still moving from left to right. And because the area is above the x-axis, it's going to be positive area. So we actually have a trapezoid there. And we do have a formula for the area of a trapezoid. That's actually base 1 plus base 2 divided by 2, all multiplied by the height. So we could use that formula, but most students don't really don't have that memorized. So we can just use triangles and a rectangle. So we already found the area of this green rectangle, but we need to add the areas of the yellow triangles. So the area of the first triangle is base times height divided by 2, and the area of the rectangle is length times width, and the area of the other triangle is same thing, base times height divided by 2, 1 times 3 divided by 2. So we get 1.5 plus 6 plus 1.5, and finally we get 9. So the area in that trapezoid is 9. So let's do a few more of these problems. Now we're looking for the area between the x-axis and the graph of f of x between -1 and -2. But notice we're actually integrating from right to left this time. Now this is this rectangle area here. But we're going from -1 to -2, so we're moving in the opposite direction. So even though the area is above the x-axis, it's going to be negative area. And so we need length times width, so the area is -3. Okay, now we're going right to left again, from 0 to -4. And that's the area of this trapezoid again, but we already found that. We found the area of the trapezoid is 9. So if we're going in the other direction, instead of -4 to 0, we're going 0 to -4. Then we just change the sign of the number. So instead of +9, it would be -9. And here we're integrating from 3 to 0, but we already found the integral from 0 to 3. So again, we just change the sign. We got a positive, or we got a negative number. So now we just change it to positive. So that was the area of this triangle. The area of the triangle integrating from left to right is -4.5 because it's area below the x-axis. But if we integrate in the other direction and find the area of the triangle, then we get a positive number integrating from right to left. Usually the area under the x-axis is negative, but because we're integrating from right to left, it's actually positive. So now we're going to integrate from -4 to 3. And so that is this positive area. If we're integrating left to right, that would be positive area. And then we're going to add this negative area. Again, integrating from left to right, area below the x-axis would be negative. So we can just use the numbers that we already found, but rather than do that, I'm going to go ahead and just calculate each thing individually. So we have the area of a triangle plus the area of a rectangle plus the area of another triangle plus the area of another triangle, which is base times height divided by 2. And so that was that yellow area. But you see this blue sign here? That should be a negative. Again, we're integrating from left to right, so area under the x-axis should be negative. So now we just have to simplify this expression. So So we have 1.5 plus 6 plus 1.5 minus 4.5. And so it looks like we get 4.5. Alright, so we're demonstrating this property here, the limits of integration reversal property, but also we're demonstrating the integral decomposition property. Now I'm going to give you another chance to take pictures of all the stuff that we've done so far. And I want you to try some problems like that. So go ahead and try part 1 and see if you can find the value of this definite integral using the graph only. We can't really use the fundamental theorem of calculus because we don't even know what the function is. So try number 8, and when you come back we'll do it together. Okay, we're back. So if you got that right, excellent. Go ahead and try number 2, and when you come back we'll do it together. Okay, we're back, and so the area is exactly 2. So if you got that right, excellent. Go ahead and try number 3, and when you come back we'll do it together. Okay, we're back. So if you got that right, excellent. Try number 4, when you come back we'll do it together. Okay, we're back. So -4 was the area of this trapezoid part there. Okay, so now we're going to find the area between 1 and -5. So that is starting, well, it's the area of this triangle plus the area of this trapezoid thing. And notice we're going from right to left. So the triangle above the x-axis is going to be negative area, and the trapezoid below the x-axis is going to be positive area. So the area of the, let me show that again. This is the area we're finding. So go ahead and try number 5, and when you come back we'll do it together. Okay, we're back. 1. So it's not that the area of the triangle and the trapezoid combined is equal to 1. That doesn't really make any sense in the real world. It's just that the value of the integral is 1, because some of the area is negative and some is positive. Okay, but again, when we say that area is negative, we don't really mean it's negative. We just mean that the value of the integral is negative. So now let's find the value of the integral when the limits of integration are 4 to -5. So now we're moving right to left again, and so we're starting all the way over here. So we're finding all this area, which is going to be negative area because we're moving right to left. And then we're also going to find this positive area. Usually area below the x-axis is negative, but because we're moving right to left, it's going to be positive. Okay, so go ahead and try number 6, and when you come back, we'll do it together. Okay, we're back. And so it looks like we're going to end up with a negative value, -pi/2, which makes sense because we have a lot of area above the x-axis that's negative area when we're moving from right to left. And so it ended up canceling out the positive area totally. And we were left with a negative number. Okay, so if you got that right, excellent. So you can use shortcuts. You don't have to show every single step here, every single formula. Feel free to use some shortcuts to find the answer. So we learned this property here, the limits of integration reversal property, and we also learned the integral decomposition property. It turns out there's some other properties that we are going to use throughout the calculus curriculum. One property says that if you have a common factor in all the terms in the function inside of an integral, you can take that constant out of the integral. So notice we have a c value here, and we actually put it in front of the integral. That's the factoring a constant in an integral property. Then there's the integral of a sum property. If you want to integrate the sum of two algebraic expressions, then you can actually break that into two integrals. Now, it doesn't work for multiplication or division, but for addition or subtraction, it works. So we also have the integral of a difference property. So if you want to integrate some expression minus another expression, you can integrate the first expression and then subtract the integral of the second expression. Now, how do we know that this works? Well, the definitions that is given for the definite integral is this expression here, and we're using right endpoints, so you don't have to use right endpoints. You can use any endpoints you want. But in this curriculum, we're using right endpoints. It's just convenient to do that. So if this is the definition of the integral, then you can prove these properties of integrals using that definition. Now, are you required to do that in school? No, not really. But if you want to see a proof just to know what it would look like, here's the proof of the integral of a sum property. And so you can look at that if you want to, but it's just not really necessary. You'd have to use your sigma notation rules down here, and your limit rules here, and you can kind of see why that shows that those integral properties work. So now we're going to do some more problems. It says if the integral of f of x from 6 to 8 is equal to 7, and the integral of g of x from 8 to 6 is 10, and the integral of f of x from 8 to 11 is negative 1, find the value of each expression. So we're going to use our integral properties, and I want you to take a picture of all these properties. If you haven't got a picture of those two properties at the left, the purple and green properties, take a picture, and also take a picture of these purple and green properties. You're going to need these as we do these problems. So we can't integrate 3 times f of x. We just don't know how. We don't really have the information that we need to integrate that function 3 times f of x. But we do know what the integral value is of f of x from 6 to 8 without the 3. We know, you can see up there, the integral of f of x from 6 to 8 is equal to 7. So if we can somehow change the form of this expression, we can figure out the value of the integral. We can actually take that 3 out. The reason we took the 3 out is because we don't know the value of this expression. But we do know the value of this green expression. They actually gave us that. That is 7. So if this expression is just 3 times the integral of f of x from 6 to 8, then we can find the value of our original expression. That's just going to be 21. Because this expression here, again, that's 7. So we used that rule that tells us we can pull out a constant. Now we have the difference between two functions, and we don't know how to find the value of this, but if we break it up into 2 different integrals using whatever we call that, integral of a difference property, then we'll be able to calculate. So, do we have this value? Yes, we do. It's equal to 10. But we don't have this value. We have the integral from 6 to 8. We don't have the integral from 8 to 6. So we're stuck. But remember, we can change the sign, or we can flip the limits of integration, reverse them, and write a negative in front. So this expression here is equal to this green expression. So I'm going to go ahead and maybe I'll just color code those. And this expression over here, I'm just keeping that. So maybe I don't have to highlight that. But again, we know that this is 10 over here, and the value of this expression is 7. So that became 10, and this became -7. So our answer is -17. So we're using these properties of definite integrals to find these values. So now we need to factor 1/5 out of the integral. And again, so we didn't know the value of this integral, but we do know the value of the integral from 8 to 6 of g of x. But we don't want that. We want the integral from 6 to 8. So what do? Well, we just flip it around. We reverse the limits of integration. And when we do that, we have to change the sign. So I have to put a negative in front of there. And so then we have 1/5 times negative of whatever that value would be, and we know that that value is 10. And so we simplify, and we get -2, it looks like. All right. So again, we're just using these basic properties of integration. These are going to be very important throughout the calculus curriculum. So now we're going to integrate f of x from 6 to 11, but the problem is we don't have that integral up here. But we do have the integral from 6 to 8 and from 8 to 11. So remember the integral decomposition property? I think that's what we called it. The integral decomposition property. That tells us if we want to find that integral, we can integrate from 6 to 8 and then add the integral from 8 to 11. And that equals the integral from 6 to 11. So from 6 to 8, that value is going to be 7. And from 8 to 11, that value is going to be -1. And so we get 6. All right. So now we have one more. We're going to integrate from 6 to 8. But now we have f of x plus 2 times g of x. And we don't have any information on this. We don't know how to integrate with that function in there. So what we're going to do is we're going to break it up into parts. We're going to use the integral of a sum property. So I broke it up into the sum of two integrals. But then we can take out that 2 because we don't know how to integrate 2 times g of x. So I'm going to take out the 2 out of the integral. And so now we have the integral from 6 to 8 of f of x. That's just 7. And do we have the integral from 6 to 8 of g of x? The answer is no, we don't. We have the integral from 8 to 6 of g of x. We want the integral from 6 to 8. So we just have to reverse the limits of integration and change to a negative symbol. And maybe I'll just keep that integral there for now. So that integral is 7. This integral is 10, I believe. Integral of g of x from 8 to 6 is 10. And that should be a plus sign. I don't know why I put a negative symbol. And the integral of f of x from 6 to 8 is 7. So finally we get looks like negative 13. Okay, so I'm going to leave those in the window, and I want you to try some problems. But I'm going to give you one more chance to take pictures of these properties here. So you have this property, if you haven't got a picture of that yet. You have this property, and then you have these 3 properties. So make sure you have those in front of you before you attempt this stuff. And you can use numbers 9 through 13 to help you. So try number 14. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Go ahead and try number 15. And when you come back, we'll do it together. Alright, we're back. And so we get 8 and 1/2. If you got that right, excellent. Go ahead and try number 16. And when you come back, we'll do it together. Okay, we're back. Now, if you write it like this, that's fine. It's okay to leave your answer like this, or it's okay to round off your answer with a decimal approximation. That's fine. But if you got that right, excellent. Try number 17, and when you come back, we'll do it together. Okay, we're back. And negative 4.5 plus 24 is 19.5. So if you got that one right, excellent. Go ahead and try number 18, and when you come back, we'll do it together. Okay, we're back. You could also write negative 2 pi plus 1 over 2. It's the same thing. Or you could write a decimal approximation. It's up to you. So if you got that right, excellent. Okay, so those were some properties of the definite integral. And now we're going to learn the substitution rule. You're going to need the differentiation formulas, so if you need these, you can take a picture. And we're going to do some review on the chain rule before we go into that. So let's find the derivative of this expression. The chain rule is connected to what we're about to do, the substitution rule. So let's review the chain rule. Now we can't find the derivative very easily unless we change to 5/3 power, so we haven't found the derivative yet. We just changed the form of the expression. So now we're going to find the derivative. Remember, we first find the derivative of the outside function, and that would be the power rule. So that's the power rule there. And the second step is to keep the inside function unchanged. We're keeping that. We're not doing anything with it. But then we're going to multiply all that by the derivative of the inside function. So that is the chain rule. So simplifying, we have 5/3 times x to the 5th plus 6x raised to the 2/3 power. And the derivative of that orange expression is 5x to the 4th plus 6. And in my curriculum, remember, we're not allowed to leave our answers with fraction exponents, so we have to change to the cube root of x to the 5th plus 6x to the 2nd power times 5x to the 4th plus 6, and we can just leave our answer like that. So that was the chain rule. Let's do one more example. So we're going to find the derivative of the outside function, which is the secant function. So that's going to be secant times tangent. So that's the derivative of the outside function. But the second step of the chain rule is to keep the inside function. The inside function is still going to be there. Then the third step of the chain rule is to multiply all that by the derivative of the inside function. And you recall the derivative of an exponential function is just whatever the function is times the natural log of the base of the function. And so it's probably best to write, well, you can write it however you want to write it. We always try to avoid any confusion, but it's kind of hard with this expression, to be honest with you. We could move the 3x to the front. That might simplify things a little bit. But there you go. That's the answer. So that was the chain rule. So I want you to get a picture of the information at the right. We're now going to learn the substitution rule. And the substitution rule is used to find the antiderivatives of functions that are more complicated than we usually deal with. And this is not really going to make much sense right now. Neither are these steps, so we're going to have to do some practice problems for you to see how this works. So again, get a picture of all this. You're going to need these steps in front of you and a picture of the substitution rule. So substitution is used when an expression is too complicated for us to find its antiderivatives. So we have a situation here where substitution would be useful because we don't know how to find the antiderivative of that expression. Now, in previous classes, we got around this problem by simply expanding. We just used FOIL, and we got 9x squared. Add the inner terms, we get 6x, and then plus 1. And we can easily find the antiderivative of this expression. So that was one way that we dealt with problems like that. We just changed the form of the expression. So the antiderivative of that expression is 3x to the third power plus 3x to the second power plus x plus c. So one way we can deal with expressions that are a little bit more complex is we can just change the form of the expression. But what if we have something like this down here, where instead of 3x plus 1 to the second power, we have 3x plus 1 to the seventh power. We can't change the form like we did up here and expand the expression. That would take a long time, and we could use the binomial theorem, if you recall that theorem from the previous course, but that would also be kind of tedious. So how do we do this? Well, we could just kind of guess what the antiderivative is going to be. So normally when you find an antiderivative, you add 1 to the exponent, so we can make that 8, and then to counteract, when we find the derivative, we'll write a 1/8. So now we're going to find the derivative of this expression and see if we get the original expression. So we're going to check to see if this blue expression is actually the antiderivative of this yellow expression. But when we find the derivative of this expression, we have to use the chain rule. And the reason we have to use the chain rule is because we have this inside function here. When you have a function inside another function, so we have this blue function that's inside this outer yellow function. When you have a function that's inside a function, you have to use the chain rule when you find the derivative. Now, students typically don't like using the chain rule. It comes up all the time in calculus. Very, very frequently, and students don't have to, or they don't want to have to use it over and over and over again, but unfortunately that's what you're going to have to do. So we're going to use the chain rule when we find the derivative to check to see if we get back to the original expression. So we're going to find the derivative of the outside function. So that means we're going to bring down that 8, and we're going to subtract 1. So that was the derivative of the outside function, that yellow part there. Then we're going to keep the inside function. Remember, when you use the chain rule, you keep the inside function. It doesn't go anywhere. But then you multiply by the derivative of the inside function. The derivative of the blue expression is 3. So now we have to simplify all this and see if we get back to the original expression. So let's simplify. 8 times 1/8 is 1, so that goes away, but this orange 3 stays there. And 8 minus 1 is 7, so we get this. So that was close. We found the derivative and we got almost the same thing, except we have this green 3 in front, and I don't see any 3 over here, so we have to counteract that 3, but that's okay. All we have to do is just move this over and modify the expression by multiplying by 1/3, because that'll counteract the 3 that's the multiplier. So now we're finding the derivative of 1 over 24 times 3x plus 1 to the 8th power, and we're trying to see if the derivative of this blue expression is equal to the yellow expression, and it will be. So we bring down the 8, and it multiplies into 1 over 24, and kind of cancels out that, well, it turns it into 1/3. And then subtract 1 from the exponent, and then multiply by 3, and look what happens. Now when we multiply 3 and 1/3, we get rid of those constants, and we're left with what we were looking for there. So we did it with trial and error. We kind of figured out what the antiderivative is. The antiderivative is this blue expression. And of course we have to write plus c. But you can see that that was kind of a lot of work, and we were just kind of messing around. We didn't really have a methodical way of finding the antiderivative. At least we weren't using a methodical approach there. So students wonder, is there a way for us to figure out the antiderivative of expressions like this in a more methodical way? And the answer is yes. It's called substitution. So we're going to learn that, so we don't have to take so much time to find the antiderivative of an expression like this. And I also want to mention before we proceed that this kind of demonstrates the idea that you can't just throw any expression inside this these yellow symbols and think that you're going to find the antiderivative. We can't find the antiderivative of just any function. The functions that you're going to find the antiderivative of in this course are hand-picked. They are functions that we know we can find the derivatives, or the antiderivatives of them. Now, I want you to notice something. If you find the derivative of this expression, you have to use the chain rule, and you get our expression that we started with. So that is the principle of the substitution rule. We're dealing with expressions that can be considered the result of using the chain rule. This expression over here that we started with is an expression that could be considered the result of using the chain rule to find the derivative of another expression, and we get this expression that we started with. So what I'm trying to say is that when you use substitution, it's like using the chain rule in reverse, and that's why we need substitution to help us find the antiderivatives of these expressions, because when the chain rule is involved, things become more complicated. So let's try another expression real quick here before we use the methodical approach. Again, if you look at this, you can see that that's complicated. I mean, how are we going to find the antiderivative of that? Well, we know the derivative of sine is cosine, and we know that we have the inside function. Remember, when you find when you use the chain rule, you're not supposed to change the inside function; it just stays in there. So let's try finding the derivative of this expression, and maybe we'll get lucky. So, but again, when we find the derivative of this expression, notice that we have to use the chain rule, because we have an inside function and we have an outside function. It's very difficult for students to come to terms with the fact that you have inside and outside functions. They just don't like that. I don't know why, but every student, including myself, when I first learned the chain rule, it was just very difficult. It's important for you to understand when to use the chain rule and how to use it. And the only way to do that is just to attempt practice problems. So when we use the chain rule, we find the derivative of the outside function. So the derivative of sine is cosine. That's step number 1. Step number 2 is we keep the inside function. We don't do anything with it. Step number 3, we multiply all of that by the derivative of the inside function. The derivative of this function here is 2x, and look, we got lucky. So that actually ends up being the antiderivative. Sine x squared plus c is the antiderivative, or the family of antiderivative functions. But again, we just got lucky there. We need a more methodical approach to this. And again, notice that when we found the derivative of this expression, in order to get our original green expression, we had to use the chain rule, you see. Again, what we're about to learn is how to use the chain rule in reverse, so to speak. So you can see that we need something to help us do this in a more methodical way. So now we're going to learn the substitution rule. And again, you can't do this with every function. So we have hand-picked examples where you can do this. And you're not really required to do other examples, so you don't have to worry about that. Again, you can't just pick any function. You can't find the antiderivative of just any function. So look at this expression. That's really complicated. How are we going to find the antiderivative of that expression? Now, what we're about to do is what we call changing variables. We're going to change the variables. We're going to change the x's to u's, or we're going to change this expression so that instead of being written in terms of x, it's going to be written in terms of u's. And because we always use u as our new variable, we often call this u substitution. And the whole point is to create an expression in terms of u that is easier to find the antiderivative of. So step number one is to set our new variable u equal to something in this expression. And most of the time it's going to be an inside function. So see how this green function is inside the square root? So we choose u to be x to the 6th minus 22. Now I know what you're thinking. You're thinking, well, how do we know for sure what to choose? Well, sometimes we choose the wrong thing and it doesn't work. So we don't really know exactly what u is going to be. We just have to try something and see if it works. And of course, you're probably going to ask the question, well, how do we know if it doesn't work? Well, we'll talk about that. We'll give an example of that later. So that's step number one, is to choose some expression in the integral that you're going to make equal to u. Now, here's where things are going to get really weird. Dx is ornamental. It's not a real value. It's just something that we write next to an expression we're trying to find the antiderivative of, along with that s symbol. So dx is not a real value. It's just ornamental. But when we find the derivative of u, we're going to call it du. That's really weird. That's very, very weird. I'm trying to write that legibly. I thought this is supposed to be an ornament. Now we're saying it's actually the derivative of an expression. It's the derivative of this. So this notation here, that actually means something. That's the derivative of u. But this notation up here means nothing. It's not a value. It's just something that we placed next to the expression we're trying to find the antiderivatives of. So why is that? Why are we making this, or why are we using du for our derivative? Why are we notating our derivative with du? Well, there's a reason for that. But we'll talk about that later. But again, this is very weird. But if that were not weird enough, we're going to do something that makes this even stranger. When we find the derivative, we're going to write dx next to it. Why in the world are we going to do that? Well, du, like I said, that actually means something, but dx means nothing. It's completely ornamental still. So we have a dx here that's ornamental, and we have a dx here that's ornamental. But why do we write dx over here? Well, dx is what we can call a pseudo-variable. You can consider it to be like a pseudo-variable. The reason we write dx is that when we complete the third step of this process and we solve for that pseudo-variable dx, Notice I got dx by itself. We solved for dx. We perform operations which are necessary to help us convert this this integral so that it's in terms of u only and not x. So it's just a coincidence that when we solve for this nothing pseudo variable, we get an expression that helps us to convert this integral into a u integral. So we only use it for that purpose. Dx, again, is not a real thing. It's just something that we put there to help us with the process. So this is not something that is exactly easy to understand. Again, we're using the chain rule in reverse. Using the chain rule going in the forward direction is hard enough to understand, but going in reverse, I mean, that's very, very complicated stuff. The good news is you don't have to understand the details about why this works right now. Right now you just want to learn how it works. So now we go to step 4. And step 4 is we're going to rewrite this integral, but instead of x to the 6th minus 22, we're going to write u, because didn't we say that this green expression in here, that's equal to u, right? We said that here in the blue equation. And then, you see how we have this dx here? We're going to rewrite that dx, but we're not going to write it as dx. We're going to write it as this thing that we said dx is equal to. You see that down there? So we're going to write du over 6x to the 5th power. So we replaced dx, this dx here, with all that. Now how do we know dx is equal to that? Well, because we solve for dx down here. Again, this is just a way to help us do these problems. So now we're on to step 5. Step 5 is we're going to cancel out all the x's. Now, isn't it true that x to the 5th and x to the 5th here, they cancel out? So now we're left with 1/6. I'm going to put that 1/6 in front. Square root u du. Okay, so now we get to the point where we need to stop and understand what we just did. We changed the form of this expression so that the expression is in terms of u, but now it's much easier to find the antiderivative of that expression. So that's why we did that. We changed the expression, we changed the variables so that it's much easier to find the antiderivative. That's the whole point of this. Now, why did we write the derivative of u as du? Well, as I said, we're using the chain rule in reverse, so to speak. Now, let's look at the chain rule real quick, and we're not going to go over this that much because this is kind of confusing. It's kind of an involved process, so I don't want to really go over this much. I just want you to learn how to use the distribute or the substitution rule. But just so you know real quick, if we have a function in another function, that's when we use the chain rule. So if you want to find the derivative of that expression, the chain rule says we find the derivative of the outside function, we keep the inside function, and then we multiply by the derivative of the inside function. This is a way to write the chain rule. But if you're starting with an expression, like we did up here with this yellow expression, if you're starting with an expression that looks like this, then we find that this derivative here, when we go backwards, when we go from this yellow expression here to the green expression, because that's what finding the antiderivative means, you're going backwards, right? This expression here, this blue derivative, it'll disappear. It'll just go away like you didn't even need it there. All right? So du is the derivative, just like g prime is the derivative. So du is kind of the equivalent of g prime of x. And so when you find the antiderivative, du is just going to disappear. And for that reason, you can pretend that du is just ornamental. It's not really necessary. You can think of it as ornamental, and that's why mathematicians like to call it du, is because we're pretending that it's just ornamental, even though du is not really ornamental. dx is ornamental, but du is not ornamental, but we can pretend that it is ornamental, and that's why they use that notation. So if you were wondering about that. Now again, if you're having trouble understanding everything that we're talking about, that's okay. All you need to know is how to do these problems. So now let's move on to the next step. And notice I changed root u to u to the 1/2 power. We have to do that in order to find the antiderivative. So now in step 6, we're going to find the antiderivative. And so remember, we add 1 to the exponent. And when we find the derivative of this, remember the 3/2 is going to go down and multiply into something, so we get 1/6. And so what is that something? That something is going to be 1/9, it looks like, when you solve for x. So we're going to need a 1/9 there, and then we're going to have to add c. So we found the antiderivative of that expression. So again, you can see it was much easier to find the antiderivative of that expression than the antiderivative of that expression. That's the whole point of this. Well, now we can't just leave our answer with u, so we have to put our original expression back in. Now that we found the antiderivative, we're going to take u and replace it with this expression here that we set u equal to. So we have x to the 6th minus 22 to the 3/2 power plus c. And believe it or not, this is the antiderivative of this expression. So obviously we need more practice with that. That's an involved process. There's 7 steps to the process. We need a lot more practice. So don't worry about it. We're going to get a lot of practice. But before we finish this problem, we need to change the expression, because remember, we're not allowed in my curriculum to have our final answer with a fraction exponent. So there you go. That is the final answer. That is the antiderivative of our original expression up there. So if you find the derivative of this blue expression, you would get back to this green expression here. Now, you may not believe me. You may say, well, I don't think so. I don't know if that's really true. So up here we have a check. So we can find the derivative of that expression. And if you follow along here, we have to find the derivative of the outside. So that would be the green part. Remember that if we're going to check our answer and find the derivative of this expression, that's what d over dx means. It's the derivative. We're finding the derivative to see if we get back to the original expression here. If we're going to find the derivative, notice we have to use the chain rule, because we have an inside function and we have an outside function. So again, when you find the antiderivative to get this expression, you're doing the chain rule in reverse. So we're going to find the derivative of the outside function, that's this green part. We're going to keep the inside function, that's the purple. And then we're going to multiply by the derivative of the inside function, which is this. And if you simplify all that, you get to the original expression. So is this an involved process? Yes, very involved. But the only way to help yourself to learn this is to do more practice problems. So I'm going to show what it's like, or what happens when you choose the wrong u. But for now, we're going to choose the correct u. And I'm going to show you with this particular problem what happens if you choose the incorrect u. Now look at this expression. We're trying to find the antiderivative of that expression. But that's really complicated. That's a really complicated expression. So how are we going to do that? How are we going to find the antiderivative? Well, again, we're going to change variables with the substitution rule. So we're going to let u equal whatever the inside function is, and the inside is probably going to be this expression here. Again, I'm going to show you what happens if you don't choose the right expression. That's step number 1. Step number 2 is to find the derivative of u, but instead of calling it u prime, like that, we're going to call it du, because we like that. We want that to be considered an ornament, even though it's not really an ornament. It actually represents something. And I just noticed that before we find the derivative, we need to change the form of this expression to x to the 1/2. Because remember, we can't find the derivative very easily unless we change the form. So we're going to get 1/2 times x to the negative 1/2 using the power rule. And remember, we're going to do something really weird. We're going to write the ornament dx right next to it. So you might wonder, do you always do that? Do you always write the dx next to it? And the answer is yes. It just helps us. So that was step number 2, but I'm going to simplify this a little bit and write that as 2 root x. Remember, negative 1/2 power means 1 over root x. And now I'm going to go to step 3. And I'm going to multiply both sides by 2 root x to solve for the ornament dx. That's always step 3, is you solve for dx. Alright, now I'm going to go to step 4. And that's where we take this integral and we change variables. We convert it. So I'm going to replace root x plus 3 with u. So instead of root x plus 3 to the 4th power, we have u to the 4th power. And I'm going to take this dx, you see that dx, and I'm going to replace it with what this tells us dx is equal to. Again, this is the process. You don't have to understand why it works right now. You just have to figure out how it works. Okay, so step number 5 is to cancel out the root x's. So see how these root x's cancel out? You want to cancel out any x's that you can cancel out. And we have a 2 there. And du is the derivative of u, but we can just assume that it's ornamental. We can pretend. Not assume, but we're going to pretend that it's ornamental, even though it's not, because when we do the chain rule in reverse, this du just disappears. So now we're going to find the antiderivative of that expression. So we have to add 1 to the exponent, and when we find the derivative, we're going to multiply 5 by something to get 2. And what is that? Well, obviously that's 2/5. You can do the math if you want. 5 times what is equal to 2. Solve for x, you get 2/5. So now we have the antiderivative. Step 7 is to go back to x's, because we want just x's. So what was u? U was root x plus 3. So that's our answer. That's the antiderivative. So that's the process. It's the same 7 steps. Step 1, choose u. Step 2, find the derivative of u. Step 3, solve for dx, the ornament. Step 4, change your variables. Step 5, cancel out the x's. Step 6, find the antiderivative. Step 7, go back to x's. It's the same 7 steps. So, again, I know that's an involved process, but it is necessary to use this u substitution. Again, we can call it the substitution rule, or we can call it u substitution. So again, you might be wondering, well, what happens if you choose the incorrect u? Well, here's an example where we chose the incorrect u. Instead of u being square root x plus 3, we made u square root x. And we go through the same process, and there are 2 things that happen that make it to where we realize that it's not working. One thing is that the root x doesn't necessarily cancel out. Now in this case it actually would cancel out, because if we let u just be root x, then it would cancel out. But we made root x u, so we're failing to see that those actually cancel out. You want to see very clearly that the x's cancel out. The second reason that this didn't work is, look at this expression. Let's look at it down here. That expression is no easier to integrate than this expression. This is no easier to find the antiderivative of than this expression here. Well, it's a little bit easier, but it's still not obvious what the antiderivative is going to be. So that's what happens if you choose the incorrect u, is that your x's won't cancel out, or the expression won't be easy to find the antiderivatives of. Okay, so let's try another one here. So look at this expression. That's very complicated. How do we find the antiderivatives of that expression? It's very, very complicated. Whenever you have this situation, usually we would try the substitution rule. So first we're going to let u equal the inside function. Obviously this function is inside, right? So u is almost always the inside function. And then step 2 is we're going to find the derivative using du notation. That's Leibniz notation. We're also going to write the pseudo variable, the dx, the ornament there. In step 3, we're going to solve for that ornament dx. Not because dx is an actual thing, it's just that process of solving for that non-existent value there, that's going to help us change variables. And again, the whole purpose of changing variables is to make the expression easier to find the antiderivatives of. So now we go to our integral, and we're going to rewrite that integral, but we're going to replace 3x to the 5th minus 7 with u. Then we're going to take this ornament and replace it with what this expression says down here. So that's du over 15x to the 4th. And step 5 is to cancel out the x's. The x's should cancel out. If they don't, that means we've got a problem. And you can see that the x's do cancel out. So we're left with 4 over 15 times 1 over u cubed, and then our ornament du. Now du again is not technically an ornament, but we're just pretending that it is an ornament, because when we use the chain rule in reverse, that derivative disappears. Okay, so we can't find the antiderivative with the expression like that, so we need to change the form. We're going to change it to u to the negative 3 power. Now we can easily find the antiderivative. So step 6 is to find the antiderivative. Now again, this expression is much simpler than this expression, and that's why we did this. Now we can easily find the antiderivative. So it's going to be, well, we're going to have to add 1 to the exponent. Remember, we always do that. And now when we find the derivative, we're going to bring this down in front and multiply it into something so that we get 4 out of 15. So what is that something? Well, it's going to be negative 2 over 15, it looks like, if I did my math correctly. And yes, that looks correct. So we found the antiderivative. That was easy, a lot easier than finding the antiderivative of this expression here. Okay, so now we're going to go back to x's. So we have negative 2 over 15 times whatever u is, and we see that u is 3x to the 5th power minus 7. And so that is the answer. But remember, we're not allowed to keep our answer with negative exponents. So we're going to write one final answer here. So that's going to be negative 2 over 15 times 3x to the 5th minus 7 to the 2nd power plus c. So if we find the derivative of this, we get back to that expression there. And in order, if you really wanted to check, it'd be better to use this expression here. That's easier to find the derivative, but you'd have to use the chain rule in order to check your answer. Okay, so let's try another one. So again, if you're still confused, if you're still thinking this is too complicated, well, what's the solution? The solution is do more problems. Step number 1, define u. U is usually going to be an inside function. Step 2, find the derivative of u using Leibniz notation in a pseudo variable. Step 3 is to solve for dx, the pseudo variable. So we get du over, actually 5 times du over 3x squared is equal to dx. Step number 4, we're going to change variables in the integral, so we have x squared times sine u, and then instead of dx, we're going to write what the bottom equation tells us dx is. That's 5 du over 3x squared. Step 5 is to cancel out the x's if we can, and it looks like we can, so the x squareds cancel out. Now if the x squareds didn't cancel out, you would know that you chose the wrong u value, most likely. Now again, u or du is not really ornamental, but the reason that we call it du is because we can pretend that it is ornamental, because it's just going to disappear when we find the antiderivative, because when we're finding the antiderivative, we're using the chain rule in reverse, so to speak. So the antiderivative of sine is negative cosine, and you can confirm that by finding the derivative. And so then lastly, we're going to replace u with what we defined u to be, and that was 1/5 x cubed. So there you go. There's another example. Again, if you find the derivative of this using the chain rule, you get the original blue expression. So substitution is used for expressions that are more complicated than normal. Alright, let's try another problem. Again, more practice is what you need to get this down. Step number 1 is to find, well, to define u. Step number 2 is to find the derivative of u, which we call du using Leibniz notation. And we're going to use that ornament dx. And then step number 3 is to solve for that ornament dx. And then step number 4 is to rewrite the integral and replace 1 minus 2x squared with u, and replace dx, the ornament, with what we said that our expression is equal to. So we get negative du over 4x. Step 5 is to cancel out any x's. We have 3/2. 6 over 4 is 3/2. And we need negative 3/2. And u cubed and du. So again, this expression is a lot easier to find the antiderivative than this expression here. That's the whole point of this. So now in step 6 we find the antiderivative. We know we're going to add 1 to the exponent, and when we find the derivative we're going to multiply by something to get negative 3/2. So what would that be? 4 times something is equal to negative 3/2. Do the math on that and you'll get negative 3/8. So we need a negative 3/8 in front of that. Of course, add the c value, and the last step is to plug in or replace u with what we defined u to be. And And how do we know that this works? Well, we can just find the derivative of this blue expression, and then we'll get back to this yellow expression. But we'd have to use the chain rule. So there's another problem. So we're going to do 2 more of these problems before you try one on your own. I know you're probably anxious to try one of these on your own, but you need to see quite a few of these before you attempt one yourself, because this process is pretty involved. Now here's an example where it's easy to get confused. And so I've rewritten this in this form, because instead of allowing this to turn into u to the 3rd power, we're going to make u to the 2nd power, and this cosecant is going to cancel out. That's not something that's very obvious. Sometimes it's easy to get mixed around with u substitution because there's a lot of different options. So u is going to be the inside function. Then we're going to find the derivative of u, and we get negative cosecant x cotangent x. So you should know that from your differentiation formulas. That's down here in yellow. You should have those memorized by now. And step 3 is to solve for the ornament dx. So we have negative du over cosecant x times cotangent x is equal to dx. So now we go to step number 4, which is rewrite the integral. But instead of looking at it this way, we're going to look at it this way. So we're going to replace cosecant x with u, but we're going to keep the other cosecant x. So that's kind of confusing. I'm not trying to confuse you. I'm just letting you know that sometimes these problems have little things like that that make them a little more challenging to understand what's going on. So now we're going to replace the ornament dx with this expression here, and so we get negative du over cosecant x cotangent x and notice that these x's cancel out, so you're left with, on step 5, you're left with negative u squared. So that's a lot easier to find the antiderivative of. So we have negative 1/3 u to the 3rd power plus c. And lastly, on step 7, we're going to replace u with what we set u equal to, which is cosecant x. And remember, we write the exponent between the x and the cosecant just so we don't have to write parentheses. It's just a lazy way to not have to write parentheses, but that's just what mathematicians do, so we have to do it even though it's a little confusing. Okay, so again, if we use a chain rule, finding the derivative of this expression, we'll get to the original expression. And I would encourage you to do that, to practice your chain rule, and also to verify that we get back to the original expression. So one more problem we're going to try before you attempt some on your own. So again, first figure out what u is going to be. It's usually the inside function. Then find the derivative, writing your ornament, and du is not an ornament, but we're going to pretend it's an ornament later on. Then we're going to solve for the ornament dx, the pseudo variable. You could call it a pseudo variable if you want to do dx. Step number 4, we're going to change variables in the integral. So we're going to replace 1 plus 2x cubed with u, and we're going to replace this dx with that expression there. So we have du over 6x squared. And then in step number 5, we're going to cancel out the x's, and it turns out even the 6 cancels out this time. So we have the integral of 1 over the 5th root of u times du. And before we find the antiderivative, I'm going to move that up to u to the negative 1/5 power. Remember, we don't know how to find the antiderivative when it's in that form. So step number 6 is to find the antiderivative. We're going to add 1 to the exponent. So we get 4/5. Now when we find the derivative, we have to bring that 4/5 down and multiply it into something to get 1. So what would that be? Well, obviously that would just be 5/4. It's the reciprocal. And on step 7, we're going to replace u with what we set u equal to, 1 plus 2x cubed. And remember, in my curriculum, we're not allowed to leave our answers with fraction exponents. So we're going to change that to 5/4 and the 5th root of 1 plus 2x cubed to the 4th power. So there you go. Now, I want you to take a picture of all this information. If you haven't already taken a picture, you need your differentiation formulas, you need your steps. These steps are particularly important, so please get pictures of these pages. And you can get a picture of this page. We did some practice problems. And get a picture of this page. And I'm going to leave numbers 23 and 24 in the window. And I want you to try number 25. Now, step 1 is to determine what u is going to be. Now, I want this to go smoothly for you, so I'm going to tell you right now what u is going to be. Remember, u is usually the inside function. If there's a function on the inside of an expression, that's usually what it's going to be. In the next class, we're going to find that that's not always the case, at least in certain circumstances, but in this case, u is going to be 1 plus sine x. So I gave you the answer for step 1. Allow u to be 1 plus sine x, and go ahead and try number 25. Again, you should have those steps right in front of you if you forget the steps. And you have the steps right over here for each of these problems. So go ahead and try 25. When you come back, we'll do it together. Okay, we're back. So there you go. If you got that right, excellent. If you find the derivative of this, you should get the original expression. But when you find the derivative, you're going to have to use the chain rule. So if you got that right, excellent. Go ahead and try number 26. I'm going to leave numbers 23 through 25 in the window. When you come back, we'll do it together. Okay, we're back. So there you go. If you got that one right, excellent. Okay, so we have just 4 more problems to do. I want you to do these last 4 problems so you have an idea of how this works before you do the homework, because this is, as you can tell, this is kind of an involved process. So step 1 is find your u value. Now I'm going to give you a hint. U is going to be 3 over x. Alright, now you can take a picture of all this information if you want. Let u be 3 over x and attempt number 27. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Again, if you find the derivative of this expression, you should get back to this expression here. You can verify that using the chain rule. Okay. Go ahead and try number 28. And when you come back, we'll do it together. Remember, you have to choose what u is going to be equal to. You have to choose the value of u, but we don't know exactly what it's going to be equal to. Usually it's the inside function, so try 28. When you come back, we'll do it together. Okay, we're back. So there you go. So if you find the derivative of this expression, you should get the original expression. So if you got that right, good job. Now I want you to try number 29, and when you come back, we'll do it together. Okay, we're back. So there you go. So if you got that right, excellent. Okay, so let's try one more of these. Go and attempt number 30. Remember, u is usually going to be the inside function, so see what you can do. Try number 30. If you have some problems, that's okay, but give it your best shot, and when you come back, we'll do it together. Okay, we're back. And so that is the final answer. Okay, so if you got that right, excellent. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1. And screenshot number 2. And 3. 4. 5. 6. 7. 8. 9. 10. 11. 12. But don't go before you get your homework. Remember, the homework is not optional. It must be done completely, correctly, and neatly, and kept in order in your binder. So here's screenshot number 1 of the homework. And screenshot number 2. And number 3. And here's the answers. The answers to the homework. So be sure and check all your answers. If you get the wrong answer, go back and fix what you did wrong. Remember, a homework problem with a wrong answer is not a completed homework problem. So get that homework done, and I'll look forward to seeing you in the next class.